Welcome everyone to the 2024 Vision Spectra Conference. Thank you all so much for joining us, and in this session you'll hear from Daniel Pierce, a hyperspectral imaging scientist with Living Optics. Daniel heads the applications team at Living Optics and joins us today to help viewers better understand snapshot video rate hyperspectral imaging for computer vision applications. If you have any questions or comments, you can type them right to the conference chat box that is on your screen. And if you missed part of today's session, you can always come back later and watch it on demand. That's all from me. Daniel, we appreciate you for taking the time to present at the 4th Annual Vision Spectra Conference.
Great. Well, thank you very much for having me. And thank you everyone for tuning in to Vision Spectra 2024. My name is Dan Pierce. I'm Head of Applications at Living Optics. And at Living Optics, we are building a snapshot hyperspectral video camera with the goal of making hyperspectral imaging accessible to everyone on the planet. I'm going to run through some of these terms, and the aim of this presentation is really to bring the uninitiated up to speed with what we mean by hyperspectral snapshot video rate imaging. And we're going to explore some typical computer vision examples, looking at the benefits of snapshot hyperspectral imaging in context with those examples. And we're going to end with some demonstrations that are more specific around potential applications for agriculture. And what these video systems mean for that agriculture. Okay. So before we get too far into it, and I'm aware that this is a Vision Spectra conference, so I'm not going to lecture you on how a spectrometer works, but I would like to explain where snapshot imaging fits relative to some of the other type of spectral measurement systems you may be more familiar with. And so I'd start by saying that spectral measurement covers a broad spectrum of devices, tailored to a whole bunch of different use cases, and these range from the benchtop kind of dual beam spectrometers that you might be used to in a laboratory, right through to satellite imaging systems circling around over the Earth. This isn't an exhaustive list on this slide here. I hope you can appreciate that. And I've tried to cover some of the more common examples. I'm sure if there's a favorite tech of your choice that isn't listed, you can always email me afterwards. Maybe I'll update the slides and we can put some more in there. But what I want to highlight here is the trade space that we're working in here, and that you don't get something for nothing. What we're really talking about here is different ways in which you might make choices around how you capture, distribute, and filter light onto a detector. And that's what we're playing with here. So to talk through some of those trade spaces, you can see if you take a point spectrometer, the example that we gave there was like a benchtop system or a fiber coupled system. Here you're gathering light in a single spot, a single point in X and Y, but you're gathering all the wavelengths of light for that one point. So you've got high spectral resolution potentially, but you haven't really got any spatial information. And typically these would be low temporal resolution, as we'd call it. So you get a single image over the course of some time, single point of data over the course of some time. Somewhere in the middle, we have our scanning approaches, and I've shown here a line scanner, so a typical kind of slit-based spectrometer system where we have information in one spatial axis and information in the wavelength axis. But to get an image of a scene, you would have to scan that across the scene. These are typical in kind of airborne systems or satellite-based systems which are moving over the planet anyway, hoovering up data. But I would describe this as something with low temporal resolution. It takes some time to build up that scan. Slightly different geometries for looking at, say, AO2S or any kind of spinning filter wheel type approaches where you might scan the wavelength dimension and get a whole image at the same time, but you're still scanning, right? So you've still got this gap of which you build up a hypercube over time. And what the snapshot approaches bring you is this hypercube in one go, this single snap. You get all of your data. But as we said before, it's you don't get something for nothing. And so there's some trade-offs here. And so we're typically trading off maybe signal to noise ratio or the number of spatial samples you get in the scene in order to achieve that continuous snapshot imaging mode. And there's a few approaches I've listed here, maybe mosaic images you may have come across before, light field systems. Specifically for Living Optics, I'm going to talk more about coded aperture systems. Okay, so we said before there are some trade-offs. I think it's worthwhile pointing out some of the kind of practical issues that we might have with other techniques as well before we move on to the motivations for our snapshot imaging systems. And well, if we start with the picture on the left, here you can see this is a typical kind of flight line that you might get from a scanning system. And we have to wait for the aircraft to land, pull out the hard drive, process the data, correct for the illumination variations, and start the analysis process. And as well, you've got some kind of wiggles going on here as the aircraft's moving, so you have to kind of correct for that motion as well. You can see a more extreme example of this taken from my lab looking out the window, and we have these kind of artifacts you can see here. These are people and cars driving down the road or walking down the road in places, and they end up being compressed, crushed, if you like. Particular interesting definition of a car here. So from the point of view of typical computer vision-based applications, these are more challenging to work with. And that's what we're trying to solve, right? So with our motivation for the snapshot system is to bring real-time data to people, right? To give them the ability to work with video rate data, but also to work with a vision system that they're used to, where they're used to standard images, standard video formats, and just to add in a little bit of spectral information to that process. And one of my top list items here is to make it easier to collect data in the field. So you're not limited to these blue sky days. You can see here the image of the wall with the pairs on it. It's one of the more successful images captured with a scanning system by me outside, but I still had to wait a few hours for the clouds to stop passing by and to get that kind of clear blue sky settings that I needed for my data taking. And we're hoping to change that paradigm with a snapshot system. So what does snapshot mean to living optics? For us, we are talking about a coded aperture system. There's lots of different ways of building a snapshot system. I mentioned those previously, but for us, this is what we're looking at. And the diagram top right there gives you a little sneak behind the scenes of what's going on inside a compressed coded aperture snapshot spectral imaging system. You can see the little shrimp is our definition of the real world, and the real world is this full hypercube of data. You've got wavelength, you've got spatial information, and you've got an instance in time. And with a coded aperture system, we insert this mask into the optical chain, and we then pass light through a dispersive element, in this case for us prism, and then onto our detector array at the back there. And what we're talking about doing when we talk about coded aperture systems is the computation needed to convert this smear of data at the back here back into this hypercube is what the user originally wanted. You can see an example setup of a system like ours on the table below. We have the camera itself, and it's paired with a compute brick, because that compute brick is important for the type of work that we're doing. And it's also important for the computer vision developers that are going to take the data as an output from us and make use of that. And well, to give you an idea of what this looks like, we'll set it running, and hopefully, if the video works, you'll see someone clicking on some hats. So we've got 3 red hats here in the scene. On the left-hand side, you can see a hyperspectral reconstruction into RGB from our hypercube that we're generating. On the right-hand side, you can see a preview image, which is taken from a coaxial aligned camera built into the system. So the system is really 2 cameras. One is generating hyperspectral information. The other is a kind of preview image to give people a little bit of context about what's going on in a higher resolution spatial image. You can see the spectra that have been extracted, plotted on the bottom, and then we put a color overlay on top of the preview image to highlight where we found those spectra again in the scene. And all of that's happening at video rates. So that enables you to do all the types of applications that you might have had in mind from a traditional video system, but now with this extra hyperspectral information thrown in as well. Okay, so let's go a little bit deeper. Let's look at what is happening under the hood. You can see I've got an image here on the left, which is the the scene view, as we call it. And on there, I've overlaid some little white crosses. Each one of those crosses represents a point in that scene where we're extracting spectral information. And on the right-hand side, you can see the spectra that we've extracted from that, covering the wavelength range that we're interested in. One way to represent that is with a relatively naive nearest neighbor sampling. So again, on the left-hand side here, we see the scene view, this kind of high resolution. In this case, it's shown to you raw, but if I zoomed in a bit, you'd see the Bayer pattern. It's an underlying RGB image there. And on the right-hand side, we've filled out from each one of those points, naively to its nearest neighbor, the data that we had from the average spectrum over that region. So the scene view there is this kind of raw 12-bit uncompressed RGB data, and the encoded view, as we call it, which produces our spectral data, generates around 4,000 spectral points across the image, and each one of those has 96 channels. So that's what we're extracting raw, and then you've got lots of options as to how you stitch that back together again. So to give you an idea of what that looks like, here's me walking around the car park outside the office, and I've generated an RGB cube from our original 96 channels of spectral data. So each one of those points, around 4,000, has been stitched back into the image. But it's important to note that each one of those points is sparse. So although we collect data for the middle of that point, we do not collect data for the edges around that point. It's not an average of a blob, if you like, under each one of those. But that means we can play some games. One of those games is to trade off our spatial temporal space. And so the advantages of taking data, video rates are great when you've got moving objects in the scene or the camera's moving around. But sometimes you want that high resolution picture for a nature paper or something like that, right? And so one thing that you can do with some types of snapshot images is to introduce some of that motion back in and to correct for it, to enhance the resolution, the spatial resolution of your spectral data. So that's what we're doing here. You can see in this example, we start off with a picture of a daisy in the top. That's taken from our high resolution scene view image. And underneath it, you can see the RGB reconstruction from the spectral data being generated. It starts off in this quite low resolution mode. And then as we move the camera around, knowing that the object itself isn't moving, we can start to bring back some of that resolution. So there's a trade space which we work in. And the idea behind this particular camera system is to offer that back to developers and users to work with as they see fit. Okay. So that's enough about the inside of the camera. I'm going to give you a bit of an update now on some computer vision applications, and then we'll move on to something a little bit more specific on the agricultural sector. But for now, here's a few generic examples where we've looked at improving or reducing rather the number of images needed for learning on typical machine learning algorithms. Some of the other things that you might want to do, maybe tracking, or more specifically reacquisition in our case. And we've also looked at improving object detection and classification for materials which are traditionally quite difficult to work with standard RGB cameras. So on few shot learning, we can see this is a view outside our window again. The road is there. And what we're trying to do here is classify regions in the scene based purely on their spectral data. But the point is to reduce the number of training images needed or reduce the labeling costs needed. So rather than having to have teams of people hand labeling every single frame of video data, looking for whether or not that was, in this case, we're telling the difference between our artificial grass, our concrete, the tarmac surface, or whether you want to allow a system to do it by itself. And in this case, the spectral system does that. One of the other things we can do though is we can just use that spectral data straight out the bat to improve some of the detection performance in these machine learning algorithms. And these are all using CNN-based techniques, but the example still on the right there is for an avocado detection. So we've hidden some avocados in the office. We just stuffed them in the plants, not very well there. But they are difficult enough. They're partially obscured. The texture is not so dissimilar from the plants that are around them to make it easy for a traditional RGB camera system to detect and identify them as avocados. But spectrally, it's much easier. And so just by throwing that little bit of extra information in there, you can improve the performance. There's some more demos online. A lot of these were done for some showcases that we did recently. So please do visit the website there. They'll give you some more information and examples of what's possible with these types of systems. So one of the other kind of typical generic computer vision applications that people are interested in is tracking. But I don't mean tracking in terms of following someone around inside a video stream. I think that's pretty old hat now. People have been doing that for a long time. But what about if you need to be able to come back a few days later and find that same person? The core application of Snapshot spectral imaging is all about this kind of real-time material-based object reacquisition. So I like to say that we're going beyond tracking here. In these examples, you'll see some spectral-only techniques. There are other ways to do that as well. We could throw in some of that kind of machine learning based training that we talked about previously, but for now, these are spectral only techniques. And if you were wondering, why is he showing me a video of a man walking around a car park earlier? Well, hopefully it's a little bit more obvious now. What you'll see is that I had a spectrally unique material tied to my backpack. And as I'm walking around here, in fact, there were two materials. One I've color coded red and the other one blue here, but they were non-visible to the human eye. You didn't necessarily know that they were unique by eye, but spectrally they're very distinctive. And in fact, the blue one here has turned out to be quite a good marker. The red one is confused generally with a few other materials in the background, as you can see with the noise tripping in there. But the blue one is the one that we would have chosen to go forward with that. And we've done the same test here. But this time we're testing out a zoom lens. So we're changing the scale and the position of the target within the scene. And as you'll notice, as we zoom in, as we increase that spatial sampling on the target, eventually his backpack will light up blue, and you'll be able to see that the material, that covert material, has now been detected based purely on the spectral signature. There we go, as we get a little bit closer, we'll see that light up. There we go. All of this can happen real time. And so this really moves you beyond where you would have been with say a point spectrometer or a scanning system into something where these snapshot approaches really benefit. And there will be lots of scenarios where you're not looking at a face, you're not looking at a number plate. There are things which you can't do with a traditional RGB camera. And this is where that little bit of extra information from the spectral side really benefits. Okay, so the last couple of examples here we'll go through quite quickly. Hopefully, enhanced object classification. So what can you do beyond color, right? If things from an RGB perspective look pretty similar, how do you make the most of that, and how do you still perform the tasks that you're being asked to do? So here we have a fun example. This was a day at the office kitchen where we took some carrots and a chocolate. Technically, we call it a cake, but it's really a chocolate that looks a lot like a carrot. You can even see in the reflection of the knife the same spectra coming through there. The very minor differences between the spectral signatures of those materials can be detected with these snapshot systems. Okay, so a slightly more serious example here. We've got a few hats, and those hats are normally the same kind of green tone, roughly the same color. They're made of different materials from different brands, and that enables us to differentiate them spectrally. So you can see if I start that one again, we've tagged them in the scene, and then we go back looking for the same thing. It doesn't matter what shape that object is, it's really based on the material properties. And now for something that's really quite challenging from an RGB perspective, we've got some transparent or translucent liquids, and we're going to pour them from one cylinder to another. And you can see that based on the spectral signature, the differences between the oils, the whiskey, the honey as well there at the end, a slightly more extreme signature, you can see how the information can be detected effectively. We're tracking the density of liquid here as it moves from jar to jar. Okay, I'm going to fast forward this. I think you can you get the message. Hopefully, if you want to have a look online, you'll see some of these videos as well there. Okay, so in summary, hopefully I've convinced you that there's some value in a snapshot hyperspectral system for these generic computer vision-based applications. I think there's still a little bit of time. I'm going to go into a slightly deeper dive into specifically agriculture and how we've been working with that and some of our customers there. So our work in agri-tech is focused on 3 areas. Harvesting in controlled environments where industrial processes, these plants are grown in clean hydroponic growing conditions, vast quantities of food for human consumption. That's a relatively easy environment to start introducing electronics and camera systems and things like that, right? We've also looked at crop health monitoring, so more recently vineyards, and looking for kind of early disease detection and things like that in those environments. And the last one here is yield estimation. So one of the feedback that we've had from farmers and from growers all around the world is knowing what can be harvested and when and how much will be available is critical information to them, and that's really important in their businesses. So that's what we're hoping to improve for them over the course of this summer. Let's just get this one going. Okay, so hopefully you can see here the setup on the workbench. We've got a camera system, we've got a halogen light because we need that broadband illumination, and we're trying to count these little tiny lemna plants for biomass estimation and to understand the yield that they're getting, as well as a kind of live process for harvesting those. And in the orchard and fruit picking scenarios, we've got some relatively small, in this case strawberries, occluded behind leaves. And what you can see here is some little red dots poking out. Each one of those is a partial hit of a strawberry that we're detecting. These are the sorts of things that we're looking to do where that snapshot spectral imaging can really help. You can imagine if you're moving the leaves out of the way as part of a picking process, then getting that spectral information in real time is essential. Okay, so lemna plant harvesting here. I'm going to talk you through a little bit about how we got to this point as well. So it was important for me to characterize the instruments that we had and to be confident that they were providing data that was comparable to the industry standards. And so for a lot of people, a lot of farmers out there, they'll be using SPAD meters and tools like this. But really everything basically boils down to chlorophyll concentrations in plants to determine their relative health properties. So we've done some testing with transmission-based samples. You can see here, Laura, one of the team members, has put chlorophyll dye into cuvettes here. So we've done some testing there, and we've done some measurements on lettuce leaves to build a little bit of confidence here in terms of what we're doing. You can see we have pretty good correlation between our chlorophyll metric and the SPAD meter values, and that gave us pretty good confidence that it was going to work. What we've then done here is take these tiny little lemna plants, lemna minor, and one of the issues that we had with the RGB-based system is shadow mitigation. So the shadows caused by the little lemna plants look like darker versions of a small lemna plant, and so removing that misclassification in the RGB data was really easy from the spectral point of view. We just use one of the standard kind of plant health indices, the MCRI index there, and you can see there from that little video, hopefully, that we're able to see pretty clearly the density of biomass that's in that little petri dish, and could potentially scale that up to a full harvesting approach. So more recently, the team have been out in the English countryside looking at vines. So the growers, the vineyards in the local area are keen to experiment with some new tech to effectively monitor and map the vine health over the course of this summer. The team will be going back every couple of weeks to monitor these vines, and you can see one of the main advantages here of bringing hyperspectral systems into the field and at relatively close range to these vines is that no longer are you looking at broad averages of things. You can now get to individual leaves and get live feedback on small blemishes and differences between them. We can see hopefully from this video here, you've got this kind of grayscale scene view image, a bit of context information coming in from that, and then you've got overlaid on top of that the MCRI output from the data here in this Viridis color scale. So you can see the brighter the dots there, the healthier the leaves as we're walking down the vines. And yeah, it takes about 2 minutes to get from one end of the vine to the other. So we're capturing quite a lot of data here, a couple of terabytes pretty much with every visit. And the aim by the end of the summer is to have a very large data set. One of the easy benefits, you'll notice at the start, I'm holding up a big white square, but when we notice any obvious changes in illumination conditions, it's really easy for someone just to drop that square back in again. We don't have to constantly monitor that live with our data set there. Yeah, we're going to move on before we get to the end because no one wants to wait for that. Okay, fruit counting and sorting. This is the last one on the agriculture side. So the team are currently imaging orchards and vineyards every few weeks to get this large data set of fruit production and wine production in the UK. One of the things that we're looking at for the orchards is around evaluating fruit sizing and counting while the crop is still on the tree. And the main aim here is to look at yield estimation to help the orchards know what they've got prior to picking. It's still a really labor-intensive world in orchard farms in the UK. And so one of the real advantages of that snapshot imaging comes in a little bit further down the line, where we're hoping to be able to bring in some automated picking technologies into this arena. One of the fun things that the team have looked at, in this case with strawberries, well, I'll give you a quick idea of that here, is we may be able to use standard kind of structure from motion-based techniques to extract 3D information as well as spectral data from our targets all at the same time. So you can see here, hopefully the strawberry is going to get rotated here. And that gives you an idea of the real depth of information that's coming out of these systems once you get to the high frame rates. So the final slide here is a quick recap on the benefits of Snapshot Hyperspectral video. For me, dynamic events, anywhere where you're traditionally using video, be it tracking or that kind of motion-based queuing, some of the more interesting things may be around combustion dynamics with flames and explosions, or fluid mixing, as you can see from the video we've got here. Anything that involves some of that spectral information, but in a dynamic environment, is really where these snapshot imaging techniques come into their own. You can see I'm gingerly pouring some water here into our oil solution and classifying based on that. Any kind of technique like that is really critical, along with anywhere where you need that live feedback. So anything where you need a human in the loop, some kind of feedback on maybe it's healthcare or fruit picking, as we've looked at previously. Those kind of approaches, hopefully it's relatively obvious as to how those snapshot imaging systems really benefit those. But the one for me that's a real game changer is anyone who's used to doing field portable spectroscopy will hopefully attest to, is the ability to do all the simple things that you want to do in the field. You want to adjust the focus, you want to view something from multiple angles, you want continuous imaging so that you can adjust for the varying lighting conditions with your white reference material that's out there. or just to simply point and know what you're looking at the same time as extracting your spectral data. All of those things become much easier with the snapshot systems, providing you can live within that trade space of spectral and spatial information. Okay, so that brings it to an end for me. If you have any questions, please let me know.
Thank you so much, Dan, for joining us to showcase the benefits of hyperspectral imaging combined with real-time video capabilities. To everyone in the audience, if you haven't already, you can type your questions and comments into the conference chat box, and do not worry, if you have not been answered yet, you'll be reached via email at a later date. This session is hosted by us at Photonics Media, and we certainly hope you're enjoying the 4th annual Vision Spectra conference. Thank you all so much for joining us.